Today I'm going to talk about the very high temperatures that are created behind bow shocks carried by flight vehicles and how those temperatures interact with the gas medium through which the vehicle is flying and affect the aerodynamics of the journey. Due to the very strong velocity changes that take place through a bow shock, temperatures can get up to the order of tens of thousands of degrees behind a shockwave in front of a flight vehicle, and that creates very significant changes to the properties of the gas flowing through. We'll talk a little bit about the significance of some of these processes. What's happening is you're transferring energy from kinetic to some other form of energy. You're compressing the gas and you're heating it, and you can get temperatures, say, for entry into Jupiter, where there are gigajoules of energy per kilogram coming through. You can get up to 60,000 degrees of temperature. That's obviously not going to stay as air as we know it in the form of oxygen and nitrogen molecules in those sort of flow conditions. The gas dissociates, it ionizes, and that is an important issue when you want to fly through the atmosphere. So we'll start off with effects that happen quite early on. You know that gases at any temperature above 0 degrees K store energy through their thermal motion, and as a cold gas it can move in three directions, X, Y, and Z. That gives it 3 degrees of freedom to store energy. And if you want to get it hotter, it's going to move faster and store more energy. That's what happens when you heat a gas up. If you get more than a few degrees K, though, it starts doing other things. If you have molecules, that's particles formed with multiple atoms in them, they can start shaking and vibrating. They can move in and out like masses on a spring. And the actual energy associated with those vibrations is an extra mechanism for storing energy, on top of the fact that they're moving macroscopically in one of three dimensions. This can be illustrated by this little figure here, where you see a mass on a spring oscillating. This may be one part of a molecule which is storing energy through the particles vibrating. You can see when that happens, at a given temperature, you'll store more energy, so the specific heat will increase. Now, this is representing a simple one-dimensional vibration. Of course, you can have multi-atomic molecules which can vibrate in many dimensions. This one is an illustration of a three atoms vibrating together, and the more modes there are for vibrating and storing energy, the more atoms there are in a molecule, the more energy it can store and the higher its specific heat is going to become. And that affects things. We're converting energy from kinetic energy to heat going through the shock wave, and how much that heats up, of course, is a function of how it stores the heat, how big its specific heat is. So these vibrations don't get turned on immediately. They get introduced into the gas over a temperature range which depends on which gas you're looking at. For air, it increases up to something like 2,000 degrees. And the energy storage you have also affects the gamma, the specific heat ratio for gas. For cold air, before you start vibrating the particles, has a fixed gamma of 1.4. When you get above 600 degrees or so, you start inducing more degrees of freedom. When they're fully excited, you have 7 degrees of freedom for a diatomic material, and your gamma drops from approximately 1.4 down to 1.29. So we can plot this against temperature, and you can see on the left here, 400 degrees or so, you're getting a slight departure from perfect gas behavior, gamma of 1.4, increasing continuously till 1600 degrees when you can say it's fully excited. Now these have a very significant change on the gas flow properties and lift, drag, heat transfer, everything else associated with a flight vehicle. Another thing that happens is molecules start falling apart. Oxygen dissociates quite easily. It falls apart into oxygen atoms. Nitrogen is much better supported molecule. It's tied together with stronger bonds. That will dissociate at a higher temperature range. And the temperature range, of course, relates to flight speed, when you're inducing the temperature changes through decelerating the air by putting a hypersonic flight vehicle through the air you're looking at. Another thing that happens with dissociation is it actually takes energy to dissociate a gas. So if you have two molecules vibrating like that together and you rip them apart, you have to do some energy. You're taking it from the heat of formation of the molecules, and that's being confiscated from the flow. So it's actually not totally intuitive what this process does to the density of the gas. You might think but by going from oxygen molecules to oxygen atoms, you're going to a lighter gas, the density should drop. And it would do if there wasn't an associated change on the temperature. But the fact that you have to supply energy to pull it apart, that cools the gas down a lot. And the effect of the cooling of the gas is to increase its density. So there are two counteracting mechanisms here. And it turns out that for all real processes associated with hypersonic flight, it's the cooling effect which dominates rather than the splitting the gas apart. So your density increases dramatically through the dissociation process. So if you're flying at a flight speed where these reactions are taking place, it's going to change your density ratio, and that is important because it affects your shock angles. Now if you go even faster than the temperatures or temperatures and speeds where air dissociates, you start knocking electrons off too. Electrons are very well attached to the molecules, but if you get it hot enough, they will fly off, and that again takes energy, and that changes the flow properties, once again, of your gas. And the main property here is that it will increase the density. So this sketch here illustrates roughly on the flight corridor where these things occur. Plotting velocity on the horizontal axis against altitude for where you might be flying, you see that at low speeds you've got basically a perfect gas. That's what applies when you're flying a jumbo jet around the world. You go a little bit faster, you start inducing vibrational excitation, so that's starting to reduce the gamma. That happens at maybe a Mach number of 3 or 4. So some supersonic fighter jets will encounter that regime where vibrational excitation starts to be important. Then nothing much happens to about 2 kilometers per second, except that between 1 and 2 kilometers per second, you're gradually initiating the vibrational excitation of the molecules. It's not a step change, a gradual increase in the gamma of the flow. Then around about 2.5 kilometers per second, oxygen starts dissociating. You'll notice there, of course, that oxygen dissociates earlier at a higher altitude. That's because of the lower density, gases dissociate more. Higher pressure sort of supports recombination of molecules. So you'll see oxygen dissociation becoming important at about 2 kilometers per second if you're flying at 100 kilometers altitude, and about 3.5 kilometers per second if you're flying down near the Earth. Then there's quite a big gap till you reach the velocities of about 5 kilometers per second where nitrogen starts to fall apart. So you see most of our flight range, if you're coming back from orbit, like what the space shuttle used to do, you go from 8 kilometers per second down to 0. You will cover all these effects, dissociation of oxygen and nitrogen, and then the vibrational excitation. Of course, ionization is a higher energy phenomena, and you don't generally encounter that on suborbital flights. It doesn't happen on the space shuttle. However, if you're coming back from the moon, 11.2 kilometers per second, you're just getting into the region where ionization becomes important, and that has another major effect on your flow field. So that becomes important for re-entry, for return vehicles from other planets, coming back from the moon, that sort of a application. Now, if we look at it in the context of a scramjet flight path, which forms part of the assignment here, you'll see that we don't really know exactly where we're going to be flying scramjets yet. The upper limit is set by getting enough oxygen to breathe. The lower limit is set by having so high a dynamic pressure you burn yourself apart. Somewhere in that corridor, that's where we'll be flying. And you see that's going up to Mach 10, 15, at 3.5 kilometers per second. We're well into the region where oxygen's dissociating. So oxygen dissociation will become an issue for the flight of scramjets, as will vibrational excitation, because you're way over the speed where vibrations are initiated. So they have to be part of your analysis too. We're not covering them in this course. We're giving the perfect gas analysis, but this is to give you an indication of where some of these other effects are important, and they do have to be considered if you want to do a more thorough analysis. Okay, well, the primary influence, as I said, is what happens to the density. And there's a simple test we can do, or calculation, to estimate the effect of the density changes on the shock shape. Now, if you remember from your oblique shock theory, the passage of an oblique shock reduces the normal component of velocity to the shock, and it does nothing to the transverse velocity component. The velocity along the direction of the shock is totally unchanged by the passage of the shock because there's no force in that direction. The forces act normal to the shock wave. So you can do a very simple form of a continuity equation. It's the normal component of velocity that's carrying mass into the shock, and it's the normal component of velocity after the shock that's carrying it out. And of course, they have to be equal if conservation of mass is going to apply. We're not doing any nuclear reactions here. mass is conserved. And there's a very simple calculation you can do based on this geometry, which we will include in a detailed text file attached, which enables you to see how the shock wave change, and it's very simple. Density ratio across the shock goes with the tangent of the shock angle beta divided by the tangent of the angular difference between the flow direction and the shock angle beta minus theta. So a very simple measurement of the flow of the shock angle can let you know what's happened to the density ratio. What I have on this slide is some flow visualization images taken by Schlieren Photography on the shock tubes at the University of Queensland. On the left we have a shock tube called Drummond Tunnel, which is a low-speed facility, and it produces perfect gas flow of air. So the gamma is 1.4, we can use all our simple equations to categorize that flow. It's an asymmetrical vehicle, it's a double wedge. On one side there's a flow deflection of 40 degrees, and on the bottom side there's a flow deflection of 30 degrees. You can see that the shock angles are very different. More than that, you can measure the shock angles and work out what the density ratio across them would have been, and you can see a certain value. In the right-hand figure, we have a similar photograph taken off the X2 expansion tube, which is traveling at 11 kilometers per second. The importance of it being 11 kilometers per second is that it's no longer perfect gas. We're dissociating the flow, we're ionizing the flow, we're exciting all the vibrations you could possibly imagine. And as you can see, the shock angle is very, very different. We have a 44-degree shock angle for the high speed condition, and like a 55-degree approximately shock angle in the perfect gas. So why are these? Oh, we know why they're different. They're different because we're increasing the density across it. So we can now use these measurements to quantify that difference and see what the density ratio was. Okay, so as an exercise, you can use the shock angles you can measure off the previous slide and calculate what the density ratios were associated with those two flow conditions. Another thing that the real gas effects can do is they can, well, you've already seen it changes the shock angle, which may not look like a very large change, but actually we can only support a certain angle of flow deflection with an attached shock being where it starts at the leading edge of the vehicle and carries along in a straight line. If the density ratio is too high, or if the flow deflection is too high, the shock becomes detached. And we can see some pictures of a detached shock on this slide here. On the left, again, we have the perfect gas images from what we call the Drummond Tunnel, and you can see there's a very fundamental change in the shock shape on those two left-hand images than we had before. They're not straight anymore. They're pushed off from the front of the vehicle. That's what we call a detached shock. And it has to be detached to ensure the continuity of flow, that the flow that's processed by the shock can be carried out in the space you have between the shock wave and the vehicle. For the density ratios associated with the perfect gas flow, it wasn't possible, so the shock got pushed upstream away from the flight vehicle. On the images on the right-hand side, we had reacting flow. The dissociation and ionization increased the density ratio significantly, and we were able to actually carry away all that flow in a small distance between the bow shock and the flight vehicle. So you can see that in the right-hand side, an attached shock was maintained at an angle of approximately 54 degrees, whereas theoretically you can't go more than about 44 degrees in a perfect gas at these flow conditions. In this zoomed-in picture here, you can see more precisely the fact there's a dramatic increase in the flow deflection we were able to support in the reacting flow situation.